Olá, espaçonauta! Pessoal, essa semana, sabe quem apareceu aqui de novo no canal? Ele, o Alfredo, nosso grande amigo aí, Alfredo Lopes Moraes, trouxe um vídeo incrível e um vídeo que me conduz a uma nostalgia, que é explicando aí sobre a Voyager 1 e como a NASA conseguiu recuperar as comunicações com a Voyager 1. Por que eu tenho uma ligação muito forte aí com as missões Voyager? Porque elas remontam aí o lançamento delas de quando eu comecei a entender um pouco mais e me apaixonar cada vez mais por ciência. Estava na minha época de infância. Na minha adolescência foi quando a Voyager fez aquele estrago no Sistema Solar, né? Que mostrou para a gente de fato como eram aí Júpiter, Saturno, Urano, Netuno. Então, assim, eu vivi isso na minha adolescência. Então a Voyager é uma missão que eu tenho muito carinho por ela e ela está intimamente ligada à minha paixão pela astronomia e pelo espaço. Então foi muito legal, né, o Alfredo trazer esse vídeo aqui para a gente, traduzido para o português e legendado, porque a Voyager me remete a uma grande memória afetiva, né? Então, gente, nós vamos assistir o vídeo, mas antes disso eu queria pedir a vocês o seguinte: o Alfredo é um grande colaborador do canal, faz esse trabalho aí abnegado, é um trabalho totalmente voluntário, traz esses vídeos pra gente aqui, vídeos legais, dá pra gente aprender muito com isso, né? E ainda tem o suprassumo, né? Pra quem gosta aí de ouvir um pouco da língua original que o vídeo foi gravado e poder saborear isso aí e ainda lendo as legendas em português. Então, assim, vamos lá, né, galera? Vamos dar aquele salve para o Alfredo aí e mandar aquele agradecimento para ele. Alfredo merece, não é mesmo? Então vamos lá, mandar aquele salve para o Alfredo. Vamos lá no vídeo, depois a gente volta a conversar, galera.
NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Good evening, everyone. My name is Gregory Smith from Jet Propulsion Laboratory's Communications and Education Directorate, and I'm thrilled to be your host for this very special edition of the Von Karman series, Fixing Voyager, How NASA Restored Communications with Voyager 1 from Across the Solar System. The twin Voyager spacecraft launched in 1977, specifically timed to take advantage of a rare planetary alignment of our solar system's four gas giants, Jupiter, Saturn, Uranus, and Neptune, which occurs only every 175 years. This grand tour, as it is called, produced profound scientific discoveries, and Voyager 2 still remains the only spacecraft to do close-up flybys of both Uranus and Neptune. Following their planetary missions, each Voyager headed out of the ecliptic plane of the solar system and into interstellar space, headed towards the distant stars in perpetuity. In November 2023, Voyager 1 suddenly and unexpectedly stopped sending scientific data back to Earth. Today we'll learn how the Voyager team at JPL, both current and retired, used decades of experience to solve the problem. We'll also discover, as the only spacecraft to ever operate within interstellar space, the Voyager twins continue to provide new and valuable scientific data in their 47th year since launch. To sort through the myriad of questions we hope to receive from you, our viewers, we have my friend and fearless co-host, Media Relations Specialist here at JPL, Kala Cofield. Hi, Kala.
Hi, Greg, and hi, everyone. We are so excited to hear your questions about Voyager. Our social media team is working behind the scenes to pull the questions that you send us on LinkedIn, X, and YouTube. So if you're watching on one of those platforms, you should see a Q&A box. If you don't see it, try refreshing your browser. Throughout tonight's presentation, I will give your questions, some of your questions, to our two speakers. We won't have time to answer all of them, but we will answer as many as we can. We really want to hear from you because, again, this is your space program.
Thanks so much, Kala. A quick note, Kala is in our Deep Space Network Mission Control Crow's Nest studio. So if you hear chatter behind her, that is just normal operations there as they communicate with our spacecraft in real time. We are honored to have two real JPL heavy hitters as speakers tonight. My first is Voyager Mission Manager Kareem Badruddin. Welcome, Kareem.
Thanks, it's nice to be here.
Next, we'll be chatting with Voyager project scientist Dr. Linda Spilker. Thanks for joining us, Linda.
Greg, it's a pleasure to be here.
We'll be back to chat with Linda later in the program. Now, Kareem, let's begin with you. What was the first indication that something was amiss with Voyager 1?
Well, let's have that first slide. And these are antennas at Madrid. We have antennas at 3 stations around the Earth that we use to communicate with any spacecraft out in space. These antennas all happen to be pointing at Voyager 1. On November 14th, 2023, we were expecting data from Voyager 1. And we weren't getting any data back. I mean, I guess the best way to explain it is it's like we went to the mailbox and got a letter, and it was addressed to Earth from Voyager 1. But when we opened the letter, we pulled out the piece of paper inside, and there was no writing on the piece of paper. And the problem was with one of the flight computers. If I could have the next slide. So this is an image of Voyager 1 sending a signal to Earth. And the problem with, as I said, was with one of the flight computers. If you look behind the antenna, there's a band where all of the flight computers are. So we knew that it was one of the computers there.
There must have been incredible challenges in trying to deduce the problem. How do you start that process with a spacecraft that was, at the time, over 46 years old?
Yeah, it's like our great-grandparents built this machine that worked well for decades, but they're gone, our grandparents. The machine's starting to have some trouble. So we go back, and there's plenty of good records. The problem is there's so many good records. It's like finding a needle in a haystack. There's handwritten notes in the margins of 47-year-old documents. Let me have that next slide. Things like this that were some of these handwritten, some of them typewritten. Just review so many documents to look at that the key is finding the right ones. We had one retiree who joined the team to help us, who worked on Voyager pre-launch. And we collected subject matter experts from around the lab, not people who were originally familiar with Voyager, but they were able to come up to speed and help us.
Unbelievable task. Let's pause here and check in with Kala and see if we already have some viewer questions for Kareem about this amazing, amazing problem.
We already have a lot of questions rolling in. I think this is a good one to sort of clarify the stakes. Abduli on Instagram asks, what would have happened if communications had not been restored?
Well, we wouldn't collect any more science information. We wouldn't know any more about what the status of the spacecraft is. So, my analogy of writing letters. In the letters, the spacecraft tells us, how its day was and how cold it is and how much power it has and then of course all the instrument data, all the information, science information that it might return. We would get none of that. So we would have just continued to have gotten envelopes with blank pages in them.
Well, thank goodness you fixed it. Thank you, Kala. We'll keep those questions coming, and we'll be answering many more of them later in the program. Kareem, let's get back to you. I know we are skimming past months and months of painstaking detective work, but what was ultimately the problem with Voyager 1?
So it turned out it was the flight data subsystem, and let's take the next picture. And there it is. It's about the size of a legal pad. That's a photograph, obviously, of the flight data subsystem. And its job is to synchronize the instruments and the other computers on board the spacecraft. And it essentially writes the letters that get sent back to Earth. And of course, since there was no writing on our letter, we knew that this is where the problem was. And we tried, changing hardware where we could in the flight data subsystem, but those changes didn't help. And we tried different telemetry modes, which is like asking for different information in the letters. And we saw some evidence of a software problem. Next slide. There we go. And this is a graph of the different modes, and every 10 minutes there's a different mode, and you see how in one mode the graph suddenly changes. So we knew something was happening there, and this gave us a strong indication that the problem was in software. So we modified a minimum FDS program that we found in an old document to produce a memory readout, which is basically everything that's in the computer's memory. And the key was eventually getting this memory readout. And we knew what the information should be, and so we compared what it actually was to what it should be, and discovered there was a corrupted block of 256 words, which was one integrated circuit that caused all the trouble. And in that integrated circuit were stored instructions that the computer needed to operate properly.
Once the Voyager team figured out the problem was the flight data system, how does one go about fixing that issue from 15 billion miles away?
It was a first-time event, even for us here at JPL. So most flight teams on flight projects here will test a software patch in their test bed or in a simulator. We didn't have either of those things. So we had to analyze the software patch by hand. And show me the next slide. So this is actual code. So the first number is the address. The second number is the instruction that we put at that address. And this isn't all of it, but this gives you an idea of what we did by hand. And all we could do is put multiple pairs of eyes on the result, and compare what we wanted to build to what we did build. And the really cool thing is that we implemented this software patch outside of the solar system. I mean, this is something that at JPL, we build programmable spacecraft, and so we do make these kind of updates all the time on all our spacecraft, but this was the first time that we did it outside of the solar system, and so we like to think of ourselves as space cowboys.
I'm not going to argue with it. It is an unbelievable story. Tell me about April 20th, 2024. That must have been a very satisfying day at the office.
Absolutely. So that was the day that we uplinked this code and restored communication. So we're awaiting the results of that final fix. And the solution was going to be very observable. All of a sudden, we would open a letter from our spacecraft, and that blank letter would actually have words in it. So that's a very observable thing. So the next slide shows the reaction in the room when we got that letter and there were words on it. And the gentleman with his fists in the air is Dave Cummings. He's the one who actually wrote the code.
Oh, so he must have been one of the happiest people.
One of the happiest people.
Most satisfied people in the room. Incredible. I love that photo. There's such palpable joy, and you see we've circled both of our speakers who were in that room on April 20th. Incredible. Let's go visit our friend Kala in the crow's nest over in the Deep Space Network to see what other questions you have for Kareem.
So many great questions coming in. All right, how strong is the signal that Voyager is receiving? How strong is the signal from Voyager, and how strong is the signal that we are transmitting to talk to Voyager? And as a reminder, these spacecraft, Voyager 1 is 15 billion miles away. So can you talk about the strength of that signal and how the DSN plays into that?
Yeah, so the signal's the transmitted signal is very weak. It's on the order of 20 watts, I think. The signal that we uplink with is much stronger. The signal we uplink with is 100 kilowatts. And you know, the antennas help us. The signal that's coming from the spacecraft is about on the order of a refrigerator light bulb from 15 billion miles away. The same amount of energy. And the way we receive it at Earth is with lots of surface area. So big antennas, and using more than one antenna helps us.
In fact, I could add
I think a related...
No, go ahead. Sorry.
Oh no, Linda, please.
No, it's very interesting. We're so far away, 23 hours at the speed of light for a signal to reach us here at the Earth. And by the time that signal gets to us, it's a billionth of a watt. So listening for a whisper in space, which is why we need these giant antennas to pick it up.
Well, so a related question, Sam Alexander on YouTube asks, as an amateur radio operator and amateur astronomer, is there any way for an amateur to receive the signals from Voyager 1 and 2?
You know, again, it comes down to how big is your antenna. So if you build a big enough antenna, then absolutely, because those signals are coming in the general direction of Earth. And so, you know, if you step outside and you're actually bathed in Voyager's signal. Bathed is kind of a strong word. it's touching you, so it's touching everything in its field, in its view.
Wow, we're all touched by Voyager.
There you go.
Maurice Walker on YouTube asks, why was the memory corrupted? Do we know? Was it a hardware failure?
Yes, it was a hardware failure, and you know, parts break. You know, computer parts break, and we actually, you know, have an expectation that that more parts may begin to break, just like this. So it was an electronic part failure, not unexpected after all these years.
Now,
let's leave the Q&A for now, and we'll come back with thank you to both of you for those amazing questions, and keep those terrific questions coming. We'll bring Kareem back near the end of our talk to answer some more. So keep them coming. Now, let's turn to Voyager project scientist, Dr. Linda Spilker. Linda, you've been with the Voyagers on and off since 1977. I imagine it must be incredibly challenging to choose, but could you please give us some of your favorite highlights from their decades of incredible exploration throughout our solar system?
Certainly, I'd love to do that, Greg. Well, first slide, please. The Voyager 47-year mission can be divided up into two phases. The first phase is a 12-year planetary phase, and the last 35 years have been exploring the heliosphere and on out into interstellar space. In the next slide, you can see the Voyager trajectory, this special mission launched in 1977, Voyager 2 on a slightly faster trajectory, but soon passed by Voyager 1. Both spacecraft arrived at Jupiter in 1979, just 2 years later. Voyager 1 approached Saturn in 1980, followed by Voyager 2 in 1981. And Voyager 1 was bent north out of the ecliptic plane after its visit by Saturn, leaving Voyager 2 to visit Uranus in 1986 and Neptune in 1989. Flying close to one of Neptune's moons, Triton, Voyager 2 was bent south of the ecliptic plane. If we look at the next slide, we'll see some of my highlights. It's really hard to pick between all of the great Voyager discoveries. So what I tried to do is pick out one discovery that I really liked in the 4 different flybys. And at Jupiter, it was Io's volcanoes. In the image on the left, you can see a lava flow in this picture taken by Voyager. We were so close. And on the right, you can see that blue plume at the limb, and it's actually volcanic material erupting out of Io. And if you look toward the bottom left of Io's image, you can see a fuzzy spot, and that's a volcano erupting, the material falling down in a ring around Io. Next is Saturn. Of course, Saturn's rings. In the next image, you can see Saturn's rings. And Saturn's rings were really incredible, the detail that the Voyager images sent back. Here are all these icy particles orbiting together and interacting in a cosmic dance of sorts, creating this beautiful structure. And Voyager discovered dark, finger-like spokes of dust elevated above the B ring shown here, circling around with the rings. Next comes the Uranus flyby, and in the next slide you can see Miranda. It's an icy moon of Uranus. It's only 290 miles across, and yet tiny Miranda had cliffs 12 miles high, and it even had canyons 10 times deeper than the Grand Canyon on the Earth. And we think that a giant impact hit Miranda, broke it apart, and the pieces came back together in kind of a jumbled configuration, giving us the view that we saw with Voyager. And in the next slide, you can see the final flyby, Neptune. And Neptune's moon Triton was the star of the show. A moon the size of the planet Mercury, captured object in an inclined retrograde orbit, and with these dark streaks at the South Pole, active geysers on a moon so far from the sun. And that terrain just above the cap at the pole there got nicknamed cantaloupe terrain because it looked like the skin of a cantaloupe. Well, in the next slide we can see that the Voyager planetary phase ended with a very special set of images. Voyager 1 above the ecliptic looked back and took a family portrait of the planets it could see, and one of them was this pale blue dot, a picture of the Earth caught in a sunbeam. And this was taken on Valentine's Day in 1990 and marked the beginning of the Voyager interstellar mission.
That is one of the great photographs, that pale blue dot. In 1990, the Voyager twins entered the Voyager interstellar mission. How does this differ from their previous exploration?
Where the planetary flybys were really oriented on the pictures and spectra from remote sensing, in the next slide you can see the focus was quite different, that we were actually measuring the fields and particles as we went out through the heliosphere into interstellar space. And you can see in this slide here the paths of the 2 Voyagers, Voyager 1 north of the ecliptic, Voyager 2 south of the ecliptic plane. And what it was measuring is this wind coming from the sun, the solar wind, charged particles and gas flowing at high speeds from the sun inside that dark blue ring. Next, you'll see that at the boundary of this ring was something called the termination shock. And this is the boundary at which the solar wind starts to slow down to much slower speeds. And next, you'll see that it was going through in the next portion the heliosheath. After going through the heliosheath and slowing even more, it approached the next boundary that we can see here. That's the heliopause. This whole structure is moving through space, and so the heliopause is that boundary where the solar wind comes in contact with the interstellar medium. And the 2 Voyagers just happened to be going out the nose of the heliopause, and Voyager 1 crossed into interstellar space in 2012, and Voyager 2 crossed 6 years later in 2018. Once you're in interstellar space, the first thing you encounter is a bow shock, a boundary, the very local interstellar medium. And a good analogy is like the bow of a ship going through water, and you can see the waves created in front of that bow, and this is the bow shock, or very local interstellar medium. And finally, on the far right, the pristine interstellar space. In the next slide, you can see an example of what the heliosphere would like, and this is the heliosphere in your kitchen sink. Now imagine the water flowing down creates the solar wind, that water coming out from the sun. So you've got this supersonic or fast-flowing solar wind. You can see the termination shock boundary in the water, the heliopause where the bubbles die out, and then interstellar space, which is the calm portion of the sink. And if we show a movie in the next slide, what you can see is what that heliosphere looks like in your sink. And you can see the fast-flowing water hitting that boundary of the termination shock, and finally the heliopause. So this is really a fun experiment to do.
I don't think anyone watching is ever going to do dishes the same way. I think a lot of our viewers may be surprised that the Voyager twins are still doing hard science out there. Well, what types of data are you collecting since they exited the heliosphere?
Well, in the next slide, we can see that there are 5 science instruments still operating on Voyager. And the first is the magnetometer. The instrument is at the end of a long boom. It measures the intensity and direction of the magnetic field, and we want it to measure interstellar space, not the fields generated by the power on board Voyager. The next instrument is the plasma wave subsystem. It's a pair of long antennas that actually measure the radio waves that we see in space. And these radio waves can come from huge solar events that actually reach the heliopause and go out and can be detected. The next instrument is the low-energy charged particle instrument. It measures low-energy cosmic rays, protons, electrons, and molecules. It actually can step and measure in 8 different directions. The next instrument is the plasma spectrometer. It's measuring the composition, the density, and the temperature of the plasma in the interstellar medium. And then we have the cosmic ray spectrometer, measuring the highest energy cosmic rays. These cosmic rays and particles are coming from large supernova explosions from other stars. Next, we can see at the PLS instrument, we actually have both instruments turned off now and just have 4 instruments operating on each spacecraft. And we did this for power reasons. If we look to the far right, you can see that there's a little scan platform with a series of instruments on board. And that scan platform moved, and on board that is the cameras that took all the beautiful pictures that I showed. And very early into the interstellar mission, we turned off the instruments on the scan platform to conserve power. And there's a lot of interesting science. I'll just give you a few of my favorite highlights from the interstellar mission thus far. One had to do with the cosmic rays. After we crossed the heliopause, the cosmic ray instrument saw a huge jump in the abundance of cosmic rays. In fact, we found that our heliopause is shielding us from 75 to 80% of this high-energy cosmic radiation. Wow. And perhaps that was very helpful when you wanted to go ahead and start to form a life here on Earth. A puzzle to this day from Voyager has to do with the magnetic field direction in interstellar space. We thought that once we crossed that heliopause boundary, we'd rotate from the solar direction into the interstellar direction. And that hasn't happened yet. We keep watching and wondering, do we need to get even further into interstellar space? And why didn't the field direction change? And finally, a puzzle that's coming from Voyager just today. In 2020, we saw a large jump on Voyager 1 in the plasma and magnetic field intensity. And often these jumps happen, but then they slowly, over a period of months, go back to a normal baseline value. But in this case, the jump has persisted for almost 5 years. And so we're continuing to watch with Voyager to see just what might happen. And is this an event coming from the sun? Or maybe something coming instead from interstellar space? And in the next slide, you can see another kind of artistic view of what the heliosphere might look like. And you can think of them as bubbles in interstellar space. And the biggest bubble with the 4 planets Voyager visited is on the left. And of course, Voyager is much further away from the bubble now. And you can see other smaller bubbles inside of which you have a star with its own planets. And so these heliospheres or astrospheres actually form around other stars, protecting those systems. Now, if you look at the night sky, you'll notice that it's very dark in between the stars that we can see. So with human eyes, we aren't really seeing what Voyager is seeing in interstellar space. Voyager is sailing the seas of space, and if you could see with Voyager's interstellar eyes, what you would see is the currents of the magnetic field flowing through space. You would see these shocks, these waves coming from the sun and perhaps elsewhere in the midst of interstellar space. And then the particles themselves, the cosmic rays, the electrons, protons, and all of this material, much of it coming from supernova explosions, just filling up the volume of interstellar space. So with Voyager's interstellar eyes, interstellar space is very interesting.
Linda, you have such a rich history with Voyager. What most excites you about the future of Voyager's mission?
Well, Voyager has an interesting future ahead, but in the next slide, let's just go back to the past briefly.
Yes.
And I'll show you some pictures from my time, my 12 years on Voyager for the planetary flybys. The picture on the left is from 1979. I'm seated, and we're looking over a Saturn flyby timeline, getting ready for the next planet that Voyager would encounter. And the picture on the left is after the planetary mission is over. We're celebrating the successful flyby of Neptune. And this is with my colleagues. I worked with the infrared instrument on the scan platform. And these are the other three individuals, Candy Hansen and Sue Linick at the top, Bob Nelson and myself. And I love this picture because we very consciously put our heads at the locations of our scan platform instruments. And so that's a wonderful, wonderful memory for me. In the next slide, you can see the Voyager science leadership today. I'm in the light blue shirt in the middle there. Next to me is Susie Dodd, the project manager, my deputy, Jamie Rankin, and then the other individuals are the principal investigators on the various science instruments, the leads for the science instruments, and there's also a NASA representative there as well. And now for Voyager's future, the next slide. Where's Voyager headed and what lies ahead? Well, in the coming years, as we are slowly turning off the science instruments with 4 watts less power per year on Voyager, there'll come a time when we don't have enough power to power even a subset of science instruments and point the high gain antenna at the Earth, because this takes a lot of activity on the spacecraft. And when that day comes, we can no longer point at the Earth. Then the 2 Voyagers become our silent ambassadors to the Milky Way. And they'll circle our Milky Way galaxy once every 225 million years. And also on board each Voyager is a golden record. On that record are the sights and sounds of the Earth. And if you look at the cover, there's a circle with a stylus on it, and that shows whoever finds the record, okay, you take the stylus, which is underneath the cover of the record, place it at the edge of the record, and if you play the record, that will then give you the pictures and the sounds. And we even have encoded on it the speed at which to play the record so that the sounds will sound the way that we hear them here on the Earth. Now, the records are made of gold because gold is so durable. We think the cover might last 1 billion years. Maybe the record underneath the cover will last about 2 billion years. And that's a long time, but 40,000 years from now, each Voyager will come close to another star. And if there's an alien race there, perhaps they'll find the golden record and get to see a little bit of what life was like on the Earth. And so the 2 Voyager spacecraft are clearly flying where no spacecraft have flown before. But stay tuned, because who knows what else Voyager might find as it continues its journey of discovery. Thank you.
I love that. Stay tuned. Let us, Kala, you must have dozens and dozens of questions to choose from. Let's see what viewers want to know from Dr. Linda Spilker.
We're getting a lot of questions on all 3 platforms. Thank you everyone so much for sending them. I'll start with one from the #slinging slasher on YouTube. This is a common question we get on Voyager these days. Linda, any chance of more photos?
Well, Kala, unfortunately, we had to turn the cameras off all the way back in 1990 after it took that family portrait for Voyager 1. And so, no, we don't have the power to turn the cameras back on. And there's really, the stars are really pretty tiny, so we don't have any good targets left. But unfortunately, no. The cameras are off for the long term.
Thank you. Aptem on YouTube asks, and this user clearly knows a little bit about what they're talking about. They asked if you could clarify, so the Voyagers are in interstellar space, but they're not actually out of the solar system because the they haven't exited the Oort cloud, and that's of course the sphere of cold objects where comets come from. So can you clarify how both of those things are true?
That's a great question, Kala. Voyager is outside the region controlled by the sun, where the solar wind is balanced by the interstellar medium. But it's not gravitationally outside the region bound by the sun. And the gravitationally bound region is actually about halfway between two stars, depending on their masses. So out in that region, still controlled by the Earth's or by the sun's gravitational field, are the objects in the Oort cloud, and we've discovered several of them. In fact, we think perhaps Triton is a captured object either from the Kuiper belt or maybe even the Oort cloud. So gravitationally, it will take a long time. In fact, if we go to my first backup slide, this will give you an idea of the scale of what you're talking about. So here you can see the two Voyagers, you can see the Heliopausa, and where interstellar space begins, and yet the Oort cloud, this is a scale, that's not linear. You can see how huge the Oort cloud is, and then some of the distances out to the nearby stars.
Thank you, Linda. Reza on LinkedIn asked a question that a couple of people are asking variations on. Essentially, given the distance to Voyager, how much longer would we be able to communicate with it, and will the power source on the Voyagers run out before that happens?
Well, the Deep Space Network, we've gotten very clever at combining multiple stations. So we use not only the big 70-meter dish, but the smaller 34 dishes. And I think it's very likely that the power will run out before our ability to put together all of these stations runs out.
Let's bring Kareem back into the Q&A, and if you'd like to add anything, I don't want to put you on the spot, but if you want to add anything to that.
Yeah, that's Linda has it just right, and I will add that it depends on data rate. So at the lower the data rate, the further we can be with the same antenna surface area on the ground. There's certain types of data that we will lose the ability to send soon because of the speed that we need.
Yeah, let me add just one more thing. We have our own Deep Space Network, but there are other antennas that are out there that we could possibly use. And in fact, Voyager did indeed use stations outside the Deep Space Network for the Neptune flyby. So if we really continue the mission, say, into the 2030s or something, it might be possible to sort of borrow some time and put those together with the stations we have at the Deep Space Network.
Well, we have a lot more questions about this software fix and how the team did it. Mary B. on YouTube asks, is there a specific programming language used to program Voyager, and is it hard to find people who know that language?
Well, the really interesting thing is there's no computer on Earth that uses this language, because the language, there's 3 different computers on the Voyager spacecraft, and the flight data subsystem is one of them. They each have their own custom-built hardware and their own custom-designed language. And so that was one of the great challenges in correcting this code, is writing code for a computer that just simply doesn't exist on the Earth anymore. We have built a simulator so that if we have to do this again, we've incorporated everything we knew. So now we actually have a simulation of this computer, but. Yeah, that's so no, there isn't another computer like it on Earth.
That's a big challenge.
So how do you get programmers who know how to program it?
So it's the code is written in what's called assembly language, and assembly language is something that computer scientists still study. I think most most folks who study computer science will spend time in higher level languages, but especially electrical engineers will be interested in the machine level. And that's where we live. And so talking about subject matter experts around the lab, and I mentioned Dave Cummings earlier, these are folks who know how to use assembly language. And given the instruction set, which was one of those things we had to dig out of old documents, it's kind of straightforward. It's like having, a translation guide when you're trying to speak another language.
Interesting. Another question related to the failure. We mentioned earlier that it was a hardware failure, but Muni200 on YouTube asks, do we know what caused that hardware failure? Could it have been interstellar radiation?
Yeah, that's a great question. We don't know the cause, and it could have just been, a part gone bad. I don't know if that's ever happened to you with an electronic device. Has happened to me, but yeah, I think it's quite likely that it was, some sort of cosmic radiation.
But we just don't know.
We just don't know.
Wonderful. Okay, I think both of you can field this one. Corey Swan on YouTube asks, has anyone ever calculated the quantity of coffee consumed by the Voyager team from late nights and bleary-eyed mornings of problem solving?
It'd probably keep Starbucks in business for quite some time to calculate how much coffee. That's a great question.
Yeah. We could have to make up numbers for that.
Also, I imagine the lost number of hours of sleep over issues over 47 years must be incredible, I imagine. The dedication of these teams.
Yeah, one thing I would add that's interesting is during the planetary flybys, I'm not sure why this is, but it always seems like some of the most exciting events come down late at night. For instance, I remember watching the Triton pictures come back line by line, and by Neptune the data rate was pretty low. And just, keeping my eyes open, waiting to see what the whole picture would look like in the middle of the night. So, yeah, there's some lost sleep. People would bring their sleeping bags into their offices or, drive their campers in so they wouldn't miss a single picture coming back from Voyager.
Wonderful. Laguna Electric on X asks, what's the protocol of communication between Voyager 1 and JPL? I think they're just asking maybe for a little more about how we communicate with the spacecraft.
Yeah, I use the analogy of writing a letter. It's quite a bit more complicated. I will say that every spacecraft out there is using radio signals to talk to Earth, and so at Earth we have to be able to differentiate which spacecraft is sending us a signal. So the signal starts with alternating ones and zeros so that we can pick it up at Earth. And then in the very beginning, there's things called frame headers, which describe which tell which spacecraft is sending the information. And then there's all kinds of ways that the data is organized, and this is why Voyager has a flight data subsystem. This is why spacecraft have a data handling computer, is to build the telemetry, to build the information into a form that can be understood at Earth. And by the same token, the signals we send to the spacecraft are earmarked with headers that tell the spacecraft, they give the spacecraft identity at the front, sort of like an address, right? It's so that the spacecraft, if he receives a signal, he can check whether this is actually for me or not, and won't try to respond to signals that weren't meant for it.
We have so many good questions to choose from. I am having trouble deciding which one, but we have a couple of questions coming in. One from Reza on LinkedIn and one from Franza on LinkedIn. Basically, if you had access, if you could redesign the Voyagers today with newer technology, maybe even with AI technology, what would you want to put on the Voyagers, or how could newer technologies have helped it on its journey?
You want to start, Linda, or shall?
Well, I think on the science side, we can now make instruments that are so much more capable and lighter weight that you could really almost carry, instead of 10 instruments, which Voyager initially had, you could probably carry many more sophisticated instruments to send back that information. One thing you could upgrade from Voyager is Voyager has a digital tape recorder, and certainly going to some kind of solid state recorder you could store a lot more information, and that would be probably a lot more reliable as well. And probably the computers would look quite different, and the memory would be much larger. Could hold a lot more pictures, data to use to send back to the Earth.
And the thing I'll add is I've read about processors now that can function at lower power levels. And Voyager, that's one of our biggest problems, is running out of power. So if our computers could operate at lower power levels, that could buy us a lot more time. And so that'd be a big change that I'd love to see, is having adjustments that we could make, dial down the power, and whatever trade that might result in. I'd love to make it.
Yeah, to follow up on what Kareem is saying, we're looking at a possible mission for the future, some kind of an interstellar probe that might go, maybe 500 AU, much further than Voyager. And so we need to find ways to have it easily last 50 or even 50 years or even longer. And so looking at clever technologies and ways that could keep a spacecraft running for that long is really a good idea.
And one more thing is helping the teams on the ground to maintain their understanding. So like one of our big challenges in solving this problem was we had to relearn things that the designers, knew like the back of their hand, but that information had been lost because decades had gone by with no need for it. So speaking of using AI and things like that, I'd love to make the flight team smarter and just give it more access to that information that's going to help it when problems start.
Thank you so much again to everyone for all of these questions. We have so many good ones rolling in, but I want to ask just a great simple one from Matt Pike on YouTube. Linda and Kareem, what was your favorite moment from your years working on the Voyager mission?
Wow, that is really a tough one to pick one out. Yeah, I would probably say one of my very favorites was watching those images come back of Neptune's moon Triton, and knowing that I was seeing a world that was really only a pinpoint of light in Earth's telescopes, and seeing and pondering about how could you get a world that's active that far away from the sun, and just so completely unique to see that. And then of course, as a ring scientist, there are lots of wonderful ring discoveries that Voyager made as well. But it's a tough question.
And for me, it has to do with solving this anomaly. It's hard to pick out one moment, but I can say the epiphanies that came about as we unwrapped the mysteries or solved the mysteries of how the flight computers work, and how the code is written, and how the higher level code that runs on the computers works. So just each time we solved a flight software problem, a flight software mystery, a flight software puzzle, was just such a oh my, and it gave me energy to keep pressing on. I felt like I was making progress each time I learned something like that.
Well, my friends, I hate to be the bad guy. I'm afraid that is all the time we have for tonight, our last Von Karman talk of 2024. I want to first thank my incredible speakers, Kareem and Linda. It is an honor to have collaborated with you over the past weeks on this talk and to share your work on Voyager that will continue to inspire generations to come. To my wonderful co-host, Pela, for choosing such terrific questions, and I know you had thousands of them. I am so grateful that you are on our team. Thank you.
Incrível isso, não é mesmo? Bacana demais. Ó, gente, Voyager 1, Voyager 2 é fantástico, né? E ver como que a NASA aí retomou as comunicações com a Voyager 1 é uma coisa incrível, né? Deu para aprender muito, não deu vídeo fantástico. Muito obrigado mais uma vez, Alfredo Lopes Moraes, nosso amigo e colaborador do canal Nerd aos 50, lá de Portugal, mandando esse vídeo pra gente aí. Vídeo incrível, né? E você já sentou o dedão nesse vídeo para fazer ele ir cada vez mais para frente? Não? Então vamos lá todo mundo junto, ó. Vamos lá? 1, 2 e... Isso aí, galera. Senta o dedão no like. Outra coisa, usa aí todo o pacotão youtubístico. Curte, compartilha, se inscreve aqui no canal, dá a sua opinião, né? Comenta aqui. Quando você faz essas coisas todas aí, o YouTube entende que o vídeo é de relevância e joga ele lá para cima. Vai entregando cada vez a mais pessoas. Outra coisa, curtiu o vídeo, apareceu o botão hypar, corre lá e clica no botão hypar, que isso aí é igual disparar um foguete aí para levar o vídeo lá para cima. E agora, você que curte muito o nosso canal, pode comprar hypadas, isso mesmo. Você pode colocar várias hypadas aí num vídeo, comprando as hypadas do YouTube aí, baratinho, só para dar uma força, aquela mão mesmo. Muito legal isso, né? Então vamos lá, galera. E agora eu tenho um recadinho incrível para vocês. Vou ali trocar de roupa, ali trocar de camisa para voltar para dar esse recado. Aguenta a mão aí. É o seguinte, galera. Tudo que você sempre quis saber sobre astronomia por um preço que parece impossível. Isso mesmo. Um conteúdo que vale mais de R$500 está disponível para você aqui no canal. Por apenas R$9. E não é mágica não, é isso mesmo. Para acessar o universo do conhecimento científico que você não vai encontrar em nenhum canal aberto, junte-se a Nerd aos 50 Astronomia Espaçonautas VIP e descubra uma comunidade exclusiva onde o amor pela ciência encontra conteúdo de alto nível. Aproveite a chance de explorar os mistérios do cosmos com quem entende do assunto, sem gastar uma fortuna. Chegou a hora de mergulhar na astronomia de verdade. Por menos de um café por mês você terá grupo VIP no WhatsApp. Envolva-se em discussões fascinantes e tire suas dúvidas com outros entusiastas e especialistas. Vídeos sem censura, sem comerciais. Aprofunde-se em conceitos científicos sem interrupções e aproveite áudios originais que o YouTube não permitiria. Biblioteca completa de livros em PDF. Tenha em mãos os títulos mais importantes da astronomia para expandir os seus conhecimentos. Lives exclusivas com cientistas renomados. Fique por dentro das últimas descobertas e tendências da astronomia participando de conversas ao vivo com profissionais do ramo. Cobertura de missões espaciais e lançamentos de foguetes. Assista aos eventos que moldam o futuro da exploração espacial com a cobertura de quem realmente entende do assunto. Sorteios e brindes. Participe de sorteios mensais e concorra a itens incríveis para a sua coleção. Esse é o passaporte para o universo sem precisar gastar mais uma fortuna. Não deixe essa oportunidade escapar, pessoal. Seja um membro espaçonauta VIP e tenha acesso ao melhor conteúdo de astronomia por apenas R$ 9,90 por mês. É por tempo limitado. Junte-se agora à comunidade que está transformando o modo como exploramos o cosmos. Clique no link que está na descrição e no comentário fixado aqui desse vídeo para garantir a sua vaga e comece a explorar hoje mesmo o universo. Bacana demais, não é mesmo? Estou te aguardando. Clica no link que está aqui embaixo para você entender o que é essa bagaça aí. Vem para cá ser espaçonauta de carteirinha VIP.